So far we have seen how to add two vectors and multiply a vector by a number. Now we'll have to learn how to multiply two vectors, and we will have two ways of doing that, two very different ways. One is called the scalar product, in which we take two vectors, multiply them in a certain way, which I'll just show you in a second, and we'll get a scalar, a number at the end as a result. The other way of multiplying two vectors that we'll learn about in the next video is called the vector product, in which case we take two vectors, we multiply them, we use a different symbol for this multiplication, and as a result we'll get a vector. Okay, so this is why it's called the scalar multiplication, because it results in a number, a scalar, and it's called the vector product, the vector multiplication, because it results in a vector. So let's start with the scalar product of two vectors. Let's take two vectors a and b. The scalar product of two vectors let me call them a and b, is defined as follows. It's denoted by a dot vector b. Sometimes this is why it's sometimes called the dot product. So, but we'll call this the scalar product. It's equal to the following number. It's the length of a, of vector a, multiplied by the length of vector b, which is then multiplied by the cosine of the angle between them. Okay, theta, this Greek letter, now stands for the angle between our vectors. So let me just give you a little sketch. Let's say that these are vectors a and b. Then the angle between these vectors is this angle. Okay, so again, what we'll do is we'll take the length of a, the length of b, and the cosine of the angle between them, and we multiply these numbers to get the scalar product of our vectors. Okay, so this is very important. This is how the scalar product is defined for two vectors. Now, a few things to notice is that the first one is that it doesn't depend on the order of the vectors, this formula on the right hand side. So the scalar product, just like the addition of two vectors, is commutative. You can swap the terms, the order of the terms you can change, and you still get the same number, because these things on the right hand side don't care about the order, whether it's a and b or b and a. The next thing, so let me just put that in writing. So the first remark is that a and b has the same scalar product as b and a. Okay. The next thing is, well, you might be wondering, what is the scalar product good for? I mean, what does it do for us? Well, for that we just have to look at the formula. First of all, it has the length of each vector included in it, but more importantly, it has the cosine of the angle between the two vectors. So if we can calculate the scalar product of two vectors, and we find, for example, that the scalar product, which is a number, turns out to be 0, that can only happen if one of the two vectors is one or both vectors are zero vectors, but that's not very interesting. If they are non-zero vectors, meaning that these lengths are non-zero numbers, positive numbers, then only the third term can be 0. So, and the way that can happen, so the way that the scalar product is 0 for non-zero vectors a and b being not equal to the 0 vector, which has length 0, then that means that A and B are perpendicular to one another. Meaning that the angle, their angle in radians is pi over 2. Okay, so pi over 2 radians is the angle, or 90 degrees. So they have a right angle between them, because then the cosine of pi over 2 gives us 0. So this is how we can get 0 for the scalar product of two non-zero vectors. It only happens if these two vectors are perpendicular. So this is a very good use for the scalar product to test whether two vectors are perpendicular to each other or not. So let me just put down a notation. So A and B is then at right angles. So of course, now this remark seems a bit silly, because I told you that A and B are perpendicular to each other if we find their scalar product to be 0. But how do we find the scalar product? Well, we have to know these things. So we have to know the angle beforehand if we want to use this formula. But if we know that the angle is already 90 degrees, calculating the scalar product and getting 0 at the end doesn't give us any new information. This is why we have to look at another way of calculating the scalar product of two vectors, and this other way involves the coordinates of our vectors. So let me write it here, that if A has the coordinates A1, A2, and A3, so this is a vector in space. I have these unit vectors along each of the positive axes, and A1, A2, and A3 are now real numbers, the coordinates of my vector. And similarly for B, I will get B1, B2, and B3 as its coordinates. So in order to calculate this scalar product, the dot product of A and B, well, we have to take these sums and simply expand this product, which we can do. Okay, now if we expand this product, we'll get all sorts of terms involving the scalar products of these basis vectors I hat, j hat, and k hat. For example, we'll have a term with a1 times b2 and the scalar product of I hat and j hat. Okay, so if we do this expansion, we'll have 9 terms, 3 for each of these first 3 terms. So we'll have 9 terms, and quite magically 6 of these terms disappear, turn out to be 0 because of this second remark. So remember, these basis vectors I hat, j hat, and k hat are perpendicular to each other. Which means that I hat has the dot product with j hat being 0, and similarly j hat with k hat gives us 0 as its scalar product, and finally k hat with I hat gives us 0. So these scalar products are all 0, which means that the only terms that remain are the terms where we multiply I hat by itself, j hat by itself, and k hat by itself. So let's look at those products separately. So for these vectors, when a vector is multiplied by itself, and it's probably a good idea to say that down here, that if you take a vector A and take the scalar product with itself, you will get its length squared, and what you will also get is the cosine of what angle? That the angle between a vector and itself is 0, so, and the cosine of 0 is equal to 1, so really what you get is just the length squared. So the length of I hat squared and the length of j hat squared and the length of k hat squared are all 0 because these are unit vectors. Okay, so by using these properties, what we get is a1 times b1 plus a2 plus times b2 plus a3 times b3. Now we have obtained a nice formula for the scalar product of two vectors using only its coordinates. So let me write that separately. So we have found that the scalar product of a and b can be expressed using their coordinates as a1 times b1 plus a2 times b2 plus a3 times b3. Okay, so before we finish this video, I would like you to consider the following example. Okay, the following example. Let A be the vector with coordinates 3, 2, 1, and B be the vector with coordinates -2, 3, and 0. My question, my request is for you to you calculate the scalar product and input that number that you get in the box below, and also decide whether A and B are perpendicular or not. Okay, so this is a question. So pause the video and use the boxes below to solve this. Okay, I hope you paused it and have found, using this last formula that we had, that the scalar product of A and B, with A and B given by these coordinates, is 3 times -2, the product of the first coordinates, plus 2 times 3, that's the product of the second coordinates, plus 1 times 0, giving us basically -6 plus 6 plus 0, which yields 0. So they are indeed perpendicular. They are indeed perpendicular because their scalar product is 0, and these are clearly non-zero vectors. Okay, I hope you enjoyed this video, and I'll see you in the next one.